Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Cousins in binary tree 2, Leetcode 2641. In this problem, we are given the root of the binary tree and we should replace the value of each node with the sum of all of its cousins' value and return the root of the modified binary tree. Two nodes of a binary tree are cousins if they have the same depth with different parents. Note that depth of a node is the number of edges in the path from the root node to it. Then in example 1, for the given tree, we can see that root node 5 does not have any cousins, so we replace its value with 0. Similarly, for node 4 and 9, we also do the same thing. Then for node 1, 10 is a sibling, but 7 is a cousin. So we replace it with sum of all the cousins, and in this case, it only has one cousin. So we replace it with 7. Similarly, for 10, only cousin it has is 7. So we replace it with cousin value 7. But for 7, we have two cousins, that is 10 and 1. So we sum them up, that is 11, and we replace 7 with 11. So that's how the whole tree is modified and returned as an answer. Now this problem wants us to replace each node's value in the tree with the sum of all its cousins' value. By definition, cousins are nodes that are on the same level but with different parents. So that means we need to calculate the sum of nodes at each level, that is the level sum. And we can use DFS or BFS for that, but BFS is more suited. I have already covered BFS on the channel, please check it out. Here we need to apply the BFS on tree, also called level order traversal, and calculate the sum level by level. I will be sharing the dedicated video for level order traversal in the coming days. Now coming back to our example, we have three levels and level sum for level 1 will be 5, level 2 will be 13 and level 3 will be 18. And once we have calculated the level sum, the challenge is not to replace node's value with the level sum, but level sum minus node's value and its siblings value if it exists. Getting this information requires access to the parent node because in binary tree, only parent node has information about its children. And one way to achieve this will be to store child to parent mapping. So now for any child, we can just go to the parent and calculate the sum of its children. Let's call it sibling sum. And now to calculate the cousin sum, we can just subtract this sibling sum from the level sum. However, a better approach can be that while calculating the level sum, if the node has children, we can add up their values to calculate the sibling sum and store the sibling sum along with the child in the sibling sums map. Then for each node, we can get its level and corresponding level sum and subtract the sibling sum. So now our solution becomes two pass. In first pass, we do the computation of level sums and sibling sums, and in the second pass, we modify the tree. So let's see this in action. Before we start the first pass, let's store sibling sum for root node. And because root node is the only node at its level, sibling sum will be equal to 5. So node is 5 and corresponding sibling sum is 5. Now we start the BFS. In first BFS pass, we will traverse the tree and fill up the list with level sums. At first level, level sum will be 5. So we store it in the level sum list and then we add its children to the sibling sums map. Node 5 has two children, 4 and 9. So their sibling sums will be 13. So we will be storing this sibling sum along with the children in the map. So for node 4 and 9, sibling sum will be 13. Now we go to the next level. In the second level, level sum is 13. So we store it in the level sum list. And node 4 has two children, 1 and 10. Their sum is 11. So we will store this sibling sum for node 1 and 10. Similarly, node 9 has one child, 7. So its sibling sum will be 7. And we will be storing corresponding sibling sum in the map. And now we are done with this level. So we go to the next level. Finally, this is the last level. And level sum here will be equal to 18. So we store it in the level sum list. And we don't have any more children. So we don't have to calculate any sibling sum. So our first pass is now complete. Now in the second pass, for each node, we will compute sum of its cousin's value by subtracting node sibling sum from level sum. Now we again start the BFS. And first node is root node, that is the node with value 5. And we can see that for this level sum is 5 and corresponding sibling sum for node 5 is 5. So we will get node's cousin sum value as 5 minus 5 equal to 0. Now we go to the next level. Here the label sum is 13. First we process node 4 and corresponding siblings value for node 4 is 13. So we will subtract 13 from 13 and get 0 again. Similarly for node 9 also we will get 0. Now we come to the last or third label. Here label sum is 18. And for node 1 corresponding sibling sum value is 11. So we'll subtract 11 from it and we will get cousin sum equal to 7 for node 1. Similarly for node 10 corresponding sibling sum value is again 11. So we subtract 11 again from 18. So we again get cousin sum as 7 and we replace node 10's value with 7. And finally we come to node 7. Sibling sum is 7. So we subtract it from 18 and get value as 11. So that's how the whole logic will work. Now let's jump into the code part. First, let's initialize a queue for the BFS or label order traversal. And in Java, we can use linked list implementation for that. Now let's also initialize label sums to store the sum of values at each label. And here we can use array list implementation because then we can treat label as an index and then getting the value from array will be O of an operation. Let's also create map to track sum of sibling values for each node. Now we can start the BFS with source being the root node, so we will enqueue it. And because root is the only node on its label, let's also add root's value as sibling sum for the root node. Now we will start the first iteration of BFS and we will run it till the queue is not empty. And because we have to go label by label, first let's get the number of nodes at the current label. Let's call it label size and it will be equal to queue.size. And once we have this snapshot, we can run the loop on it and dequeue this label and enqueue its children into the queue if they exist. Let's also define label sum to track sum of node values at the current label. Now we traverse all the nodes at the current label. First we pull out a node from the queue and add its value to the label sum. And now we try to get the sum of its children. Let's call it sibling sum. Now if the node is left child, we will add it to the queue for the next label. And because we have access to this left child, we will also update the sibling sum for the left node. We will do the same thing for the right child as well. And now we have calculated the complete sibling sum. So we should put it into the map. So if the left node was not null, we will add sibling sum to sibling sums map for the left child. And similarly, if right child is not null, we will add sibling sum for the right child as well in the sibling sums map. And finally, when we are done with this label, we add this label sum to the list of label sums. And now our first pass of BFS is complete. So we will clear the queue. That is, we will empty the queue and again add the root node to start the BFS. Let's also define the variable label to get the label sum from the label sums array. Initially, label will be equal to 0. And now again, we can start the BFS. We will again get the queue size because we are running the BFS or label order traversal label by label. And now we can get the label sum for the current label just by the label index. And because we are using array list, the time complexity for this operation is O of 1. And now we will process the current label. First, we will get the current node at this label. And now we will calculate the cousin sum. So it will be current label sum minus the sibling sum for this node. And once we got this cousin sum, we will replace node's value with this cousin sum. And now we will add left and right children of the current node to the queue so that we can process the next label. And once we are done with this label, we will increment the label counter by 1 so that we can process the next label. And now we are done with the second pass of the BFS as well. And if we have done everything correctly, now the tree would have been modified and so we can return the root of this tree. So that's it. Now let's run this code. Looks like there is a typo in the sibling sums map. I should be calling it sibling sums rather than sibling sum. Now let's run this code again. Awesome. Let's submit this code. Cool. In terms of time complexity, it will be O of n, where n is the number of nodes in the tree. And the reason for this is we are visiting each node only twice, that is in 2 BFS passes. And in terms of space complexity, it will also be O of n because we are storing each label in the queue. And in the worst case, the last label in the tree can be half the size of the tree. So it's proportional to n. Also, we are storing sibling sum for each node in the hash map and storing the label sums in the list. So because of this, the space complexity is also O of n. So I hope this video was useful to you. If it was, please like, share and subscribe. The code link is in the description below. If you have any questions or suggestions, please write them in the comment box. Thanks for watching. See you next time.